All right, so we're going to be covering about 5 different high-level topics. Some of these Brannis alluded to in the first session, so we'll be elaborating into them in a little bit more detail. So OpenMP gives you the ability to describe how you want computation to be parallelized. And we talked about the for construct in the language. Here I've given an example of what it might look like if you're doing it in Fortran, where we said it's the do construct, and all of the directives take the form of comments in the source code that then apply to the code similar to the pragmas in C. And when you say you want a for construct to apply to a loop, you're saying please distribute the iterations of this loop onto the threads and have them be executed. So by default, the compiler is going to do some assignment of iterations to threads, but you might want to control how that assignment happens. And this is where the schedule clause comes in. And it's just one of the other clauses that goes on the OpenMP pragma. And there's a wide range of schedule clauses. And this is where you get to make decisions about what the compiler is doing. It's not just the compiler doing something random on your behalf and trying to guess what's right. So we have static, dynamic, guided, which is a specialized form of dynamic, runtime, which allows you to do some experimentation and basically some feedback-driven things, possibly even inside of your application, and then auto, which then passes control back to the compiler and lets it do its best choice. So let's walk down these and talk a little bit more about why you might want to use them and what they actually mean. So the top one, static, there's actually 2 different forms of static, and if you paid attention to the first talk, you might have actually noticed both of them were shown. So the default form of static without the chunk clause basically does a even distribution of chunks of the iteration space to threads. And this is typically good if you're looking for cache locality and you have data that's distributed maybe in an array and you want to take sections of the array and assign it to a single thread because there's some kind of locality between adjacent array iterations. And maybe you would run into false sharing problems if you don't do it that way. So by default, if you have n iterations and p processors, it assigns chunks of size n over p to each one of the threads. So for 100 iterations and 4 threads, it assigns the first 25 iterations to thread 0, the next 25 to thread 1, the next 25 to thread 2, the next 25 to the last thread. If you give a chunk to the static clause, instead of doing kind of block distribution, it does the cyclic or the interleave distribution. So static comma 1 basically is a simple round robin distribution of iterations to thread. It assigns iteration 1 and then iteration 2 to the next thread, iteration 3 to the next thread, iteration 4 to the next thread, and then comes back and goes iteration 5, 6, 7, 8, 9, 10, 11, 12, and goes round robin to the different threads. That can have some nice properties too. It's very simple to implement, doesn't require a division operator. You can have wider chunks, like maybe you want to assign 2 iterations at a time to a thread, 3 iterations at a time, etc. The dynamic mode is basically saying, I have a lot of variability in the cost of each one of my iterations. And therefore, if I don't have the threads compete and grab an iteration when they're ready, I'm likely to get into a lot of load imbalance. Dynamic assignment is relatively expensive because it requires some kind of synchronization for the threads to figure out who gets the next piece of work. And therefore, sometimes you use a chunk parameter, which just says, don't just grab 1 iteration, grab 2 or 3 or 4 or 10 or some number as an atomic unit to assign to your thread. But the dynamic is basically how people typically fix load imbalance problems if they have one. Guided is a specialized form of dynamics for large iteration spaces. Basically is an optimization that says if you have a big pile of work, when you first grab work out of the pile, you can take a big chunk of work because there's a lot of work left for the other people to divide up. So maybe initially you'll take a quarter of all the work and say, I'm going to go work on this, and then the other threads go and compete for the other 3/4. And then the next thread comes in and I'll take a quarter of what's left. And then I'll take a quarter of what's left, and I'll take a quarter of what's left. And then as the pile of remaining work gets smaller, which means you're getting to the end of your iteration space, the amount of work assigned to each thread itself gets smaller. So at the very end, maybe you're only assigning one piece of work to each thread because you're trying to basically balance out at the end of the iteration space that all the threads fill in any gaps and arrive maybe at the barrier for the end of the loop at the same time. So this is one way of using kind of a dynamic dispatch mechanism, but controlling the overhead, because the more times it has to dispatch the work, the more overhead there is, but you still want good load balance at the end of the loop. Schedule runtime was added to the language, I think primarily to allow experimentation. This was sort of its first purpose, is that people didn't really know what their program was like. They didn't know the cost of the iterations. They wanted to try parameterized studies of their program. So they said, well, is static going to run faster? Is dynamic going to run faster? What chunk size should I be using? How many experiments can I do? And the runtime schedule allows you to control the schedule for your loop via an environment variable so that you can easily run your program multiple times, just change the environment variable without recompiling your program, see how the performance changes, and then once you find the optimal value, you can hard code it in the schedule clause and then submit your program for a production run. Since then, it's been extended a little bit to allow kind of dynamic feedback inside of the program, where you can use API calls to set the schedule for the next loop if you need to compute that. And then, as I said, auto at the bottom is just declaring that the compiler gets to make its own choices. And some of the auto clause enables implementations to do things that are very sophisticated, because it gives the compiler a little more control. One of the sophisticated things that some of the teams are thinking about is to take a dynamic schedule, run it once, record what the answers are from the first dynamic schedule, and then instead of doing the next one dynamic again, just reuse the same schedule that it figured out the first time. So if you have a lot of variability in your iteration space, and that gives the implementations the chance to build algorithms like that. I don't know of any systems that are actually shipping with that, but that's the mechanism which allows the implementations to do so. So I said the runtime clause allows you to dynamically change what the schedule is on a loop, and here's the API calls that allow you to set and get the current schedule that's going to be applied when you use the schedule runtime on your loop. All of the examples we've shown so far are relatively simple in how they express the iteration space. It's usually over an integer space from 1 to n, 0 to n minus 1, something like that. That was fine for Fortran. Initially, OpenMP was defined only on the Fortran language. It later evolved to C, evolved to C++. And C++ has a lot of more powerful capabilities that need to be supported. So recently, in the compiler updates, random access iterators work just as well for your index variable for your for loop as does a simple integer iteration space. So given you have the ability to choose what schedule to use, how do you think about why you want to choose one of these schedules? And it all boils down to load balance. Parallel computing does not work well unless all of the threads executing work have roughly the same amount of work assigned to them. Otherwise, some go idle, some execute a little bit long, and you don't get the kind of speedups that you might want. So if you look at the picture down here, assume each one of the bars is an iteration of your loop, and the length of the bar kind of represents the cost to execute that iteration. And what I'm illustrating here is a triangular iteration space. Like if you're doing some kind of dense matrix computation, there may be cases where you do have triangular loops, and therefore the cost of what happens in each one of these iterations is very different, and in this case is actually predictable, because it goes from relatively small to a much bigger at the end. The left picture, your left, is what you might get from a simple static distribution. It says if I have two processors and I want to partition up my iteration space and assign half of the work to each processor, I might assign the left half to one processor and the right half to another processor, the red and the blue. This would actually be a very bad idea because the area in the red is much smaller than the area in the blue, and whatever thread is executing the part in the blue is going to take a lot longer to get done with its work, and the thread doing in the red is going to hit some kind of barrier synchronization, sit there spinning its thumbs and just wasting time. One common thing, if you don't want to go to a dynamic schedule, which is one way of solving this, is to go to the static interleaved schedule, which is like static comma 1, which is to assign round robin, assign every other iteration. Now, instead of having all of the cheap ones in one thread, all of the expensive, we sort of propagate through the iteration space and even out the work between the two threads. So you get roughly the same amount of work in aggregate, even though the work in each particular iteration is quite different. One trick that does sometimes help and is necessary is that if you have a huge discrepancy in the amount of work you're doing, if it's at all possible to put the expensive things at the front of the iteration space, load balancing usually works a lot better. It's very easy to fill in the end of your iteration space with small tasks and kind of even it out, but if your very last task is bigger than all the rest of the tasks before it, you're never going to solve that load balancing problem. The only chance you have is to execute your biggest tasks first. So some systems have even gone to the trouble of running the loop once, sorting the iteration spaces by execution time, and then in subsequent iterations preferring the sorted time over the normal or the random time. This is something, if you have a huge load imbalance, you might want to consider doing yourself. A lot of times you have uniform things, and then even the static scheduling methods work. So that tells you how you can assign iterations to threads. Earlier we talked about barriers, that OpenMP started out as sort of a SPMD fork join type of language. You forked a bunch of threads, you did some work, you hit a barrier, you forked some more, or you assigned some more work, you hit a barrier, and those barriers are expensive. So you only want to use them when it's absolutely necessary to use them. And early on, there really weren't any good techniques for figuring out when you could remove those barriers in useful cases. But after a couple revisions of the spec, which is probably 5 years ago, they came to the conclusion that there's no reason why the compiler couldn't give stronger guarantees on how the implementation works. What I'm illustrating here is that if you use the same static schedule between two different iterations which have the same iteration space, so the important thing here is it's 0 to n minus 1 in both cases, 1 to n, and it's schedule static in both cases, you're guaranteed the same assignment of iterations to threads, and therefore, since the variable a sub I, written in the first loop and read in the second loop, you're guaranteed the same iteration which wrote it in the first loop, that thread will also read it in the second loop, therefore there's no cross-iteration data dependencies between these two loops. If you were to use dynamic scheduling, you couldn't do this, because it might have randomized the assignment of iterations to threads, and therefore you would need the barrier to make sure that all the writes happened before the reads. But this is one optimization technique to basically elide the implicit barrier by putting no weight on the first loop, and therefore threads can race ahead to the second loop as soon as their part of the first loop is finished. So that covers the schedule clause, which allows you to assign iterations to threads, but as I think a question during the first session was brought up, you're not always talking about one loop. Sometimes you're talking about a loop nest. And early on, you only could apply a work sharing construct to a single loop. But there's lots of cases where you want to consider the loop nest more as an ensemble and do something with the whole thing. Now, it's always possible to manually transform your program and flatten two loops into one loop. It's sort of like, are you iterating over the rows, iterating over the columns, or iterating over the elements? Here, we've sort of got the I and the j loop. Maybe n is not very big, and you have more cores than you have maybe rows in your matrix, but you've got more columns. So there is a clause to the for which says, please do the compiler transformation you might otherwise do by hand and combine these next two loops and make them logically one iteration space that you're going to assign to the threads. So this says collapse 2, which says take the one outer loop and the next inner loop, so it's the I and the j loop, combine them together into an iteration space of size n times m, and then treat that as the iterations to assign to all the threads. This really helps the readability of your code, because if you've ever done the transformation of flattening these two loops, the code becomes unreadable, and you have little modulus and division operators all over the place that make it very hard to debug. So this was a very user-driven, user-requested feature that the committee was asked to consider and did get added to the language. So that was nested loops. When OpenMP was first defined, there was a lot of discussion about software engineering and about combining different modules and how do you express parallelism in different places. And the committee thought we had this solved. OpenMP allows you to create parallel regions and then create other parallel regions inside of them, and the language does allow them to nest and correctly specify all of the right behavior. I think in retrospect, it turns out this was one of the things that was a bit optimistic. Yes, it works. Is it useful? I'm not quite as convinced. But let's talk a little bit about how it works. If you have two parallel regions, you create a certain number of threads in the outer parallel region, and then each one of those threads creates additional threads when it has an inner parallel region. You can, there's all sorts of control variables and API functions to manage how this works. The OMP set nested is one of the environment variables, or the OMP nested, OMP set nested API call that basically says, do you want this multiplicative effect to happen when you have nested parallel regions? Quite often the answer is no. Maybe you want to assign all of your threads at the outer parallel region and only use teams of size 1 at the inner. Maybe you want to use half of your cores at the outer one and half of the cores at the inner one. So there's a little bit of setup you need to do to make sure that it's running right. The OMP numthreads environment variable has been extended to allow comma-separated lists so that you can specify the number of threads at each level if that's what your program structure is. So let's look pictorially at what this might mean, and also why maybe it doesn't work as well in practice as people were hoping it worked when it was first invented. So initially we have like processor 0, which is running your master thread, and you encounter your outer parallel region, and let's assume we're going 4 wide at this point. So you create 4 threads and assign them to processors 0, 1, 2, and 3. And then each one of those threads creates another parallel region. And this time, let's assume it's size 2. So now we have 8 cores in use, and each one of our original parallel regions threads created another nested parallel region, and then they execute, and then you get down to the end of the inner one, they join, the end of the outer one, they join, and then it gets down to the next instance of a nested parallel region. And the question is, how is the assignment of threads to cores happening in this case? You would kind of want things to be uniform, but due to scheduling delays, the fact that teams are created dynamically, that doesn't always happen. So for a long time, users didn't have mechanisms to control this. Specific vendor implementations created extensions, usually environment variables, that describes these affinity mechanisms, pinning mechanisms. OpenMP 4.0, which Bronis is going to talk about tonight, finally standardizes a lot of those mechanisms and gives implementation writers and users a standard language with which to express some of these things. But the useful thing to think about here is that when you're using nested parallelism, you have to have a global view of your entire program, which sort of breaks the abstraction barriers that we thought we were solving, because you have to reserve some of the threads and processors at the outer region because you're going to use them later. And that's not really what people thought they wanted from nested parallelism. They just want to say, I want to create some work, and then later on I want to create more work. and I just want it to be added to the pool and dynamically scheduled. Nested parallelism doesn't quite work that way, even though it's well defined and can be used if you want to specifically assign these threads go to these processors, later on these other threads go to those processors with some of the extensions. But there are other techniques, and we'll get into those that do tend to work a little bit better. So let's talk about arbitrary tasks, because maybe that's what people were trying to use nested parallelism for. The simple forms of OpenMP tend to work on counted collections. Like maybe you have an array, you have a matrix, you have a loop over some counted iteration space. And like we said, for C++, you can now use the random access iterators to specify those iteration spaces. And that works reasonably well. But sometimes you don't really have a loop you need to partition across your processors. You've got different blocks of code. Or maybe there's not exactly a counted loop. There might be a while loop. There might be a recursive structure. There might be something else which is sort of your dispatch loop for creating work. And the question is, can OpenMP express those things too? So let's talk about the first approach that was introduced into OpenMP, which is just a sections construct. This is just to say, if you have several blocks of code in your program, maybe they're entire function called trees that are very expensive, but they're all independent, and there really isn't any loop that you can partition among your threads, you might implicitly create a loop over those things by using sections to say, well, this statement is my first loop iteration. This other statement is my second loop iteration. This last statement is my third loop iteration. So you can kind of think of this as a loop with 3 iterations, and then it behaves a little bit like the for loop as in assigning all of those iterations to the threads. Now, this is definitely not as scalable as using a loop, because if you're going from 1 to n, you can just increase the number n and you get more iterations and therefore can take advantage of more cores. But if you don't have any choice, this does allow you to introduce a little bit of parallelism into your code. And this actually does tend to work fairly well with nested parallelism, because since you have a static number of actions you want to perform here, you might create your parallel region with 3 threads. And you have 3 tasks. You partition them, and then you can reserve all of your remaining threads to do maybe parallel loops inside of those 3 tasks. But this is a very static way of thinking of decomposing your program into chunks, where the chunks can be assigned to different threads. Abstraction is very common. Program modularity is very common. They create boundaries where you want to think locally inside of each piece. But a lot of the constructs in OpenMP kind of force you to think a little bit more globally. They're saying, I'm going to create a team of threads. How many threads do I want? What's the work I'm going to be doing? I'm going to nest another team. How many threads did I use before? Therefore, how many threads do I have left to use? What that led to was kind of the notion that maybe thinking in terms of threads is not the kind of flexibility people want. Maybe they want a little bit more flexibility to think maybe in terms of just the work units and let the system figure out almost everything about how those work units are going to be assigned to threads. So that led to an extension to OpenMP that was introduced several years ago called the tasking extension, which integrates arbitrary tasks into the work sharing model that it had before. So let's talk a little bit about what that looks like. Here's both in the C and the Fortran form, again, which is just say, given a block of code, just wrap it in a task, and then if that's encountered inside of a parallel region, it's going to have deferred execution where eventually it will get executed by some thread. So you don't have to worry about a lot of the scheduling. You can just say, here's all of my tasks, and then the runtime system goes and partitions them to each thread. So this is kind of like a more extreme form of dynamic scheduling, where it's not just saying my loop and my iterations are static, and the assignment of iterations to threads is dynamic. This is to say I'm going to potentially randomly scatter tasks throughout my code that I know can be independent, and I'm going to wait for threads to pick them up and have them executed. Now, once you identify a piece of code that can be executed by some thread, you have to figure out what's the data environment that that piece of code is going to be executing in. In the serial program, it's the set of values and memory locations that were active when the task was encountered. If you're going to defer execution of that task and possibly have it move to another thread, you somehow have to encapsulate that entire data environment and those variables and allow the compiler to package them up so it can move them to another thread. And that's where the data scoping clauses come into play, and the mechanisms by which the compiler can pick up this piece of code and allow it to be moved to another thread. So let's talk about one of the use cases I mentioned for why you might want to use tasks. And this is the one where you've got a piece of code, you know there's a lot of parallel work in here, but you don't have a counted loop. Well, before tasking was implemented, the common way of doing this was to execute this loop twice. You would execute it once, where you'd walk the list sequentially and just count up how many elements are there in the list, and maybe change the list into an array, and then you'd run a parallel loop over the array and partition it. That gets really old really fast if you're doing those transformations. So this particular approach looks a little funny, but allows you to do the same thing with very minimal modifications to your program. Now, the top of this is the same as we saw this morning, OMP parallel, that just says create a bunch of threads. But the next thing it does, OMP single, says turn all of those threads off but one of them and put them to the side. So we're actually executing this entire parallel region on one thread. And you can think of this as kind of a dispatch loop. Its sole purpose is to create works for the other threads to do. So it's kind of a master-slave, producer-consumer type of arrangement that we're going to arbitrarily pick one of the threads as our dispatching thread, everyone else is our worker threads, and we're going to use the single to do that, and then we're just going to execute a piece of sequential code, like we're going to walk through our linked list, and we know that processing each element of our linked list can happen in parallel because all of the elements of our list are independent, but we know walking over our list has to be done sequentially because you have to be at one node before you can get to the next node. So here we have our loop over the elements done sequentially, and then every time we get to a new element, we declare we've got a task, and the task is to process the body of that element. And now we have a parallel loop over, or parallel iteration over a while loop, which is something before we introduced tasking really wasn't possible in OpenMP. So let's talk about another couple examples of where this might be useful. Here's a little game. It's a variant of, I guess, the Sudoku puzzle, where you're trying to get all of the numbers to fit together. And you might say, well, how can we apply parallelism to this particular problem? More than likely, in your real job, you're not solving Sudoku, but you may have something which has a structure equally complex as this. So let's say we start at the top and we say, I want to go parallel. I'm going to create my dispatch loop, which is what the OpenMP single is for. And then, since we're doing a Sudoku solver, we're taking kind of the naive way of doing it and just do generate and test. So we try to choose a number for a cell, and then we evaluate the board to see if it's reasonable. If it is, we commit and then choose the next number. Otherwise, we throw it out and try over. So we have the OMP task, which starts work on a new copy of the Sudoku board. We spawn a bunch of those tasks, and then we can end up waiting for them to finish so that we can figure out which one we want to commit and go on. So this solver is recursive. It sort of picks a cell, tries to evaluate it. If that's correct, it picks another cell and recurses down, tries to evaluate it, and it kind of builds a search tree where each level creates a number of tasks. Those can execute in parallel. Once those are done, it recurses down and goes to the next level. Using the tasking primitive allows you to express that kind of very dynamic, more messy type of parallelism there. Okay, so I think this sort of is a simpler way of stating roughly the same thing I was doing. You create your dispatch loop for solve parallel, and then inside of solve parallel, that's where we actually have the task construct. One of the interesting things here is that task and single are in different functions. Normally, what OpenMP did is that the loop and the pragma attached to the loop were right next to each other so that the compiler could see both of them at the same time. Here, we've allowed separate compilation. We've allowed kind of separation of interest, that the parallelism is specified in one function or one file, and the task is specified in an entirely different file. This does open up a few more possibilities for software composition, because now you don't have to statically bind things together quite as much as you did before, and you can put your tasks where they need to be. This also is kind of a preview into some of the data sharing clauses, where I said you had to encapsulate a task into a self-contained environment so that it could be moved to another thread. First private is one of the good mechanisms for doing that, which is to just say, take all these variables, make a private copy, and then make sure their initial value is the same value that the program had when the task was enqueued. So that's how you create these kind of private environments. And then at the bottom, here we're kind of iterating over different parts of the board, trying different alternatives in parallel, and then the task wait just says, I don't want to continue in my algorithm until all of those tasks that I spawned have finished. So it allows you to do a little bit of synchronization inside of the tasking pragmas. Now, from a performance standpoint, you're giving up a little bit of performance for the flexibility of specifying arbitrary tasks. One place you're giving up flexibility is that you're dedicating one of your threads to basically be the dispatch thread. And if it's dispatching, it's not doing work. After it's done dispatching, most implementations change the dispatch thread into a worker thread so that it then executes the stuff it enqueued earlier. So that usually doesn't hurt that much. If your work inside of the task is big enough, you can amortize the scheduling overhead. If it's not, this suffers from all of the same problems of any other form of dynamic scheduling, that you spend all of your time scheduling and not enough time working. So if you're going to use techniques like this, you have to make sure that the actual work inside of your task is big enough to amortize the cost of packaging them up and the cache misses to move them to another thread. But in this case, we were able to figure out that the work was big enough and got reasonably good speed up out of this approach. So launching tasks is how you get more parallelism, but you have to control how that parallelism works in order to get correct answers. So depending on how you're partitioning your data space, you may need to cause all of the tasks to stop before they go on to the next stage. If you have a barrier in your code, any tasks that were launched prior to that barrier are guaranteed to finish before the barrier goes on. And basically any thread which checks into the barrier logically becomes a worker thread to go and execute one of those tasks to get it done so that it can proceed after that barrier. If you don't want a full barrier, which is across all of the threads in your parallel region that you created, that's when you use kind of the task wait. And the task wait just says, for the dispatch thread, all of the tasks that thread enqueued have to be finished before that thread can go on. If there's other threads that are enqueuing work, those don't wait. If there's children of those tasks, they may or may not wait. It doesn't explicitly wait for them, but if there's a transitive relationship where parents wait for children, it logically waits for them. But it really just waits for all of the work that it enqueued itself. Okay, let's talk a little bit about more in detail. And one of the trickiest parts of tasking is figuring out this data scoping environment, figuring out how do I package up my task into something that can be safe to isolate and run someplace else. And because this becomes rather detailed, the compiler has a lot of rules about what it does by default, and they're usually right. They're sometimes a little bit arcane, and as Bronis was describing earlier, there's a lot of special cases about what to do with different types of variables. So for the tasking, so OpenMP has the notion of shared variables and private variables. Those establish the data environments for each one of the threads, and the tasking inherits from those environments as it makes the rules of what's to happen at each one of the tasking pragmas. Okay, so if you have a parallel region which has shared variables, those are going to be also shared for the task inside or lexically inside of the parallel region. If they're private outside, they'll become first private inside of the region. It helps to walk through an example here to talk about some of the different cases rather than to talk about it in words. For tasks, one of the differences is if it's an orphan task versus not. If the task is not lexically inside of the parallel region, it's treated a little bit different than if it is inside. So let's walk through an example. Here we have a bunch of variables, A, B, C, D, and E, that are declared at different scopes in your program. So A is a global variable, basically a static variable in the program. B and C are local to the function foo. B, and here we have two nested parallel regions, just to show that it's possible. In the outer parallel region, B is shared. In the inner parallel region, B is private. So the inner parallel region sees the outer copy, but it throws it away and basically allocates a new overlay copy that's private inside of the inner parallel region. So now B and C are treated a little bit differently. Inside of the parallel region, we have D, which is now private to the parallel region because it's allocated on the stack inside of the scope of that parallel region. And then we get down to the task. So we've got this relatively complex data environment that's been instantiated when the task is being enqueued, and the question is, if the task accesses these variables, under what rules or what assumptions can it make? So there are certain things that happen by default. So if you just say pragma OMP task, the compiler will do something, and it will try to do something reasonable. So let's see what it actually does. So for the variable A, it's shared in the outer parallel region, it's shared in the inner parallel region, the task is lexically inside of both parallel regions. So A is just going to be shared by address. So all tasks which are dispatched from this point are going to reference the same copy of A as if it were shared between all of them. If you had a big read-only data structure, this would be entirely perfect because it allows each one of the tasks to read that data structure with basically no extra cost. Okay, when we get to B, B is the one which initially was shared in the outer parallel region, became private in the inner parallel region, and now we get down to the task, and it says each thread of the inner parallel region has its own copy of B, therefore each thread might have a different value stored in B, therefore when I enqueue a task, I better make sure to grab a copy of that variable for that thread so that when I actually get around to executing it, I'm executing it on the right value of B. So it becomes first private. It's private to the task, and it needs to encapsulate and inherit the value from the thread which was outside. C is on the stack because it was allocated in the function foo, but it was allocated outside of the parallel region, which means all of the threads in the parallel region are referencing the same version of C. It wasn't privatized. So for the purpose of the task, A and B are really identical. Both of them access the same variable. So by default, C is shared. D was the same as B. It's a private variable to the thread. It was allocated in an inner scope, which is logically the same as using the private clause, so it's treated the same way. And then E is allocated inside of the task, so by default it's just private. And it follows the same rules, which means E is actually uninitialized or undefined what its value is. It doesn't have an initial value, and it's assumed that the task itself is going to assign an initial value to that particular variable. It's just uninitialized storage for use inside of the task. Something reasonable happened to each variable, but something different and for a different reason happened to each variable. And what we find a lot of times is it's too confusing to remember all the rules. And so the easy answer is just put default none on the parallel region and add your own scoping clauses. And once you put default none, the compiler will keep issuing error messages until you list exactly what you want to do with each variable. So this is kind of a good teaching exercise where the compiler knows what variables it has to disposition, and it's up to you to say, I want this one to be first private, I want this one to be shared, you can do it wrong, but at least you have control over that. So let's talk a little bit about how tasks are scheduled onto threads. And there's a couple different options here that are available in current implementations. There are other options that were just standardized in the OpenMP 4.0 spec last month, which really don't have implementations yet. And Brannis will go into some of the future stuff tonight, so I'll try to limit this to the stuff that is available in the compilers today. Okay, so tasking was added to the OpenMP language as an evolution of the standard. We started out with SPMD thread teams. Create a team of threads. We very quickly went to worksharing constructs, which is say, given that team of threads, how do we partition work and assign it to those threads for the duration of those work units. Tasking introduces a different concept. It's the concept of saying, don't assign something now, defer it so that whoever's available can pick it up later. And so it kind of breaks the notion of thread ID. When a task starts executing and you call OMP get thread num, what does it return? Well, it returns the thread which is executing that task right now. So there is a correspondence and a merging of the two models, but there's also the possibility that what if a task migrates from one thread to another thread during its lifetime? Is that a good thing or a bad thing? Like, is it okay for OMP get thread num to return two different values when you call it twice? If you're using that value to index into another array, the answer is no. You really want it to always, that as soon as you execute a task, it's going to stay on that thread until the task finishes. Sometimes you don't care. You really want dynamic load balancing. If a thread's going to block, you want it moved to another thread so that it can finish later and kind of act as a continuation. So because of that, OpenMP introduced two different variants of tasks. One of them is called a tied task, and one of them is called an untied task. The tied task means that when a thread is dispatched, it will always execute on that thread until that task is finished. If a task is untied, it may start on one thread, but if it hits a synchronization or a barrier which deschedules it, it might finish its execution on another thread. And for untied tasks, you have to be very careful not to rely on some of the API calls that are bound to specific threads. Like OMP get thread num might return a different value when you call it at different points in its lifetime. Thread private variables, which is another of these OpenMP features. It's like taking a global variable and replicating it so that each thread has its own copy of a global variable. You can declare that and the compiler can do it. Those also don't work quite right in untied tasks because you're accessing different instances of that global variable for different threads. Locks don't work in untied tasks because when you acquire a lock, the lock is owned by a thread. It's not owned by the task. So there's some pretty strict limitations in what you can do if you use untied tasks. And I think I ran ahead to this slide. So most of the time, it's safer and easier to use tied tasks, where once a task starts, You want it there until it finishes, and if you have enough tasks in the system, there's usually enough parallel slacks where that's not a big deal. If you need to start optimizing it and allowing tasks to move around, then you might want to consider using an untied task, but that's more of a advanced use at your own risk type of feature. When you start using tasks, because of the way you use them, there is a problem with potentially creating too many tasks. Like, for example, there's a simple mathematical problem for calculating Fibonacci numbers. And it has a very nice little formula that says a Fibonacci number is the sum of previous Fibonacci numbers, and you can create a huge tree and you can create tasks to create prior numbers, and eventually you create a lot of tasks. But you don't really want more tasks than you need parallel slack to keep your CPUs busy. So at some point, you basically want to turn off the creation of tasks and says, I've got enough tasks. Maybe in your tree search or your tree evaluation, you want to create tasks for the top 5 levels, the top 10 levels, and at that point you've got enough. And the if clause is one of the ways that you can say, don't create a task right now. So you can pass a variable into the if clause on the task that basically says, execute this now or defer it and execute it later. If you execute it now, you're temporarily turning off parallelism so that you can stop it from exploding and creating more tasks than you actually need. But it's a dynamic mechanism where you can make that decision based on the workload, on the data set that you loaded in. Another variant similar to the if clause is the final clause. The if statement says either for this particular task, execute it now or defer it later. The final clause basically says for this dispatch thread, stop deferring tasks even if you execute more tasks underneath it down the call tree. So it basically says I'm bottoming out at this point. I've got enough parallelism. I'm not going to enqueue any more parallel work later on. There are some ramifications to whether you execute something now versus you defer it later. And due to implementation artifacts, it was thought best left undefined what some of these differences are. It allows for faster implementations. For example, if you say if 0, that says execute it now. So if you're going to execute it now, the question is, are you required to create the binding environment for that task, or can you just execute it in the binding environment that the thread currently has? It's cheaper if you don't need to actually package it up to a separate task just to execute it now, but there are a few places where it can cause different semantics, and this example at the bottom is one of them, which is to say, if you package this up into its own separate environment, actually enforce the first private clause, I is then isolated from the original thread, and therefore when you print the value of I, it's either got the value 3 or it's undefined at that point. If you don't package it up into a separate environment and just execute it as is, it obviously has a value 4. So there are controls in the language about whether the compiler is allowed to merge data environments so that it can do this kind of optimization at lower cost, or whether you want to force it to always create the isolated data environment, always get that result because your program's sensitive to making sure that that data environment's always created. Okay, I talked earlier about synchronization for task, which is sort of like a little mini barrier that says just wait for all of the tasks that you've dispatched to finish before you go on in your particular thread. And I talked to you about untied tasks that said, how does a task migrate between different threads? Well, Taskyield is one of these migration points. And here's a little example which kind of gets into some of the very low-level OpenMP style programming where it's using a lock, it's using Taskyield to basically say, well, if I'm still waiting to acquire this lock, I don't have anything useful to do, so I'll give up my CPU and let some other thread be scheduled on this particular CPU. If this was an untied task, when it comes back from the Taskyield, maybe it would be assigned to another thread. If it's a tied task, it's guaranteed to be assigned to the thread that it was on before it yielded. But this kind of allows a very, very fine-grained dynamic scheduling to occur as part of the tasking mechanism. If you have a lot of tasks, if you have the tasks spin without yielding, there's a possibility you may end up into a starvation situation, because if every task is spinning waiting for a result for a task that's deferred and hasn't executed yet, none of them are going to make forward progress. But with Taskyield, it releases that thread to execute one of the other tasks, and you can get forward progress again. So we've got two, let's get into NUMA optimizations, and then we'll get into a closely related thing of the memory model. Okay, so I think it's been pretty clear that the simple uses of OpenMP allow a lot of power into the software developer's hand, because you're controlling what the compiler does with very minimal specifications as to how it does it. Now, this is really nice for productivity, but most people in this room actually care more about performance than productivity. So you have to start worrying about how these things actually execute on the hardware. Shared memory parallel machines come in different flavors. They come in different architectures. They're arranged different ways. And one of the common ways of building these machines is the NUMA paradigm. And that basically means that memory is sometimes closer to one core than it is to another core. And therefore, the cost of variable access changes depending on the association of memory to processor. And for high-performance systems, you sometimes have to be very aware of this. Now, NUMA effects are not caused by OpenMP. They're caused by the hardware on which it's running. If you're writing pthreads, you've got NUMA effects, because where your variables are allocated and where they're referenced depends on the cost of getting to them. But since OpenMP systems are designed to work on these kinds of hardware, you get the effects when you're using OpenMP. So let's talk a little bit about architecture. What do these machines look like? We've got a main memory. The main memory has a certain bandwidth rate with which you can access it. That's usually the slowest in the system. It's got a cache. Caches are associated with CPUs, and there's a much faster path between the cache and the CPU. So memory which is in your CPU's cache is obviously much faster than memory which is in main memory or somebody else's processor's cache. And obviously, if it's in your registers and the compilers figured out how to bring that closer, that's even better. So shared memory systems always give you the right answer, but they sometimes give it at a different cost. And earlier in the examples, we talked a little bit about false sharing, of saying, well, if you have variables different threads want to access on the same cache line, the threads are going to fight over them. And that's a bad thing. So you want to spread out your variables as much as you're able to. It wastes a little bit of memory, but it saves you a lot of performance when you do that. So pictorially, what you end up with is in the main memory, you have one cache line. It goes across the bus. All the threads are requesting it. And if each one is touching a different element of the cache line, it ends up bouncing around all over the place. So in general, what that means, or what was shown earlier, private copies of things for OpenMP is a very good idea. Semantically, you may not need to, but from a performance standpoint, it's a little bit like MPI. Things work better when you have your own copy, therefore you don't have to worry about somebody else messing you up with it. The places where there's indications of this is that if you're partitioning an array, look to see how you're partitioning it, and if you're trying to take something which is allocated close together in your index space and trying to spread it out, that's usually not a good idea. Row versus column order in matrices is typically important. Fortran and C are obviously different, but you want contiguous memory assigned to the same thread. and discontiguous memory regions assigned to different threads as much as possible. And the last point is one that was brought up earlier, but can't really be emphasized enough. Read-only memory is your friend, or even read-mostly memory, like it's modified in one phase, but it's read-only in the next phase. Shared memory systems love read-only memory. Like if you're loading a model into the application, and every thread needs to work on the same model, and it was just initialized once when it was loaded, that's a wonderful situation for sharing, because the caches can allocate parts of that model that you care about. They can throw it out, they can go back and get it, and it's as if that model were sitting in the caches of each one of your cores, but you didn't have to do anything about it. If you were doing MPI programming, you all of a sudden have to copy that model to each one of your processes and use n times as much storage to do it, whereas for shared memory systems in OpenMP, that doesn't have that problem. We know to avoid cache effects, that's almost serial optimization, but how does that relate to NUMA effects? So with a NUMA effect, you've got variables that are on different cache lines, but the pages that those cache line lived were allocated in different DRAMs on the motherboard of your shared memory node. And the question is, which DRAM was it allocated into? So in the previous picture, we had basically one big blue box for memory. All the memory was sort of uniform. Here, it's non-uniform, that the first two cores are more tightly bound to the left memory, and then the right two cores are more tightly bound to the right memory. So there's a little bit lower cost to access memory which is close to you. And if you have this code on the left where you're allocating an array with malloc, and then you're executing an initialization function on this, the question is, which memory will that array be allocated to? And this is somewhat operating system dependent, but there are some common paradigms that OSs have adopted, which basically is that whoever touches that memory first is where that page is going to be allocated. So in a parallel system, a lot of times memory is allocated in the serial initialization phase at the start of your program, and then right after you allocate it, you initialize that memory, and maybe you just have a simple serial loop to do it. What that means is that whatever thread was executing the initialization, you're forcing all of the memory pages to be allocated in the blue memory bank for that thread. So that later on, if you want to access that array from the other threads, all of it has to be remote and go to the place where it was pinned by the first touch policy. So the solution to that is to do your initialization in parallel. The malloc function returns a uninitialized memory buffer, typically. Sometimes it touches one or two of the pages to initialize some status bytes, but for the most part, it just reserves a piece of memory that you then have to go and initialize later. If you can initialize the memory with the same loop structure and the same schedule that you're going to access it later, it pins those pages to the threads that you're going to be calculating with that data later. Previously in the barrier section, we talked about using the no-wait clause to eliminate a barrier between two loops if the computation was aligned. This is another case where we're trying to align computation to threads so that the thread which initialized it is going to be the thread that uses it later. So if you're running into NUMA effects, there are some placement techniques that are coming in OpenMP 4.0 that have vendor-specific extensions usually now. They're being standardized, but there's vendor-specific knobs that are usually available. But this kind of first touch policy is another more portable mechanism for trying to enforce this. And placement matters. It hurts performance if you do it wrong. It helps performance if you do it right. So for the stream simple vector assignment computation, we had 3 different experiments being run in the green, the blue, and the red lines as the number of threads increases. The green line, which is kind of the worst performance of the bunch, had a simple serial initialization, and that was forcing all of the pages for that particular array to be bound to the master thread. And then there's different kinds of bindings of how do you assign threads to, or OpenMP threads to cores in the system. There's a compact binding and a scatter binding. Usually there's multiple threads per socket, and then there's multiple sockets. So the difference between scatter and compact is, do you prefer the threads to all live on a single socket, or do you prefer them to be spread across multiple sockets? And there's pros and cons to the two depending on how you're accessing memory. In this particular case, what we see is that the blue, the compact binding, which is to pull all the threads to different cores on the same socket, doesn't tend to help that much until you get up to using all your sockets, because that's really what's happening here is that as you increase the number of threads, you're pulling in cores from other sockets as you're going up. In the scatter binding, what it's showing is that memory was pushed out to all the different cores, pushed out to all the different sockets, was spread out across all the different DRAM chips on your system, and you're getting maximum bandwidth that your system's capable of doing. So on systems that are NUMA architecture, this is one optimization that sometimes makes a difference. There are lots of optimizations that make a difference, and usually you have to get them all right if you're wanting to achieve highest performance. So this is a sort of abstract cartoon talking a little bit about what some of the things you might need to do to get right in your application to achieve highest performance. If you don't do NUMA optimizations, you may have one limit you can hit because you're always bottlenecking on that particular memory bus. If you do the optimizations, you can get up to the next level where you're running your memory buses in parallel. On the CPU side, maybe this is the right-hand side, if you use the vector instructions, you get one level of performance. If you can figure out how to use the FMA hardware to fuse the multiplies and adds, you can get to another level of performance. If you do all of that and perfectly schedule the pipeline and the cache, you get to an even higher level of performance. All right, so let's switch from performance more to the memory model. This is sort of more technical parts of the OpenMP standard that, for the most part, it's nice to know that they exist, but it's the kind of things that you only use when you're trying to do something a little bit odd. Okay, so let's talk a little bit about the memory model. We saw kind of a machine model where we've got main memory, we've got caches, we've got cores, but OpenMP has a more abstract model that it really deals with. It deals with this notion of there's a big pool of shared resources allocated somewhere. Those shared resources can be accessed by any thread in the system, but there's also private resources that can only be accessed by that thread. Now, there's a difference between this picture and the real hardware picture, and this picture is really only enforced by convention in the compiler and in the language. And this picture is then mapped onto the system where you only have one big physical memory, and it's just being partitioned where some of it is assumed to be private, some of it's assumed to be shared. Another aspect of the OpenMP memory model is that it's actually defined to be relaxed consistency, which means that the compiler and the hardware has a lot of flexibility in how it orders computation on a very fine-grained scale. This allows almost any compiler optimization technique to kick in locally where it needs to kick in, but it does mean that if you're assuming things happen in a certain way, you might have to give the compiler extra hints that says, I really care what's happening at this particular point. And usually if you're rolling your own synchronization, you care. If you're not, let the system deal with it and you don't have to worry about this particular part of the memory model. So there's a construct called flush, which basically says align, or at this point in time, make sure that the variables that are user visible actually have the values that you expect them to have. Okay, so as I said, most of the time this is one of the hidden things in the system that it just does right. when you want to push the boundaries a little bit, sometimes this becomes visible. One of the compromises that OpenMP took when it was first invented is that OpenMP was more of an exercise on standardizing spelling rather than inventing a new language. Prior to the creation of OpenMP, there was half a dozen different parallel languages. Everybody had a different spelling for what a parallel region was, what a loop was. It was kind of a Babylon chaos. And most of the value in creating OpenMP in the first place was just getting all of the different users, all of the different vendors to agree, how are we going to spell this idea? How are we going to spell that idea? And there was a little bit more to it than that, is that there was actually some slightly different semantics in the different implementations. And in order to get the standard ratified, every time there was a difference in implementation that we couldn't work out, that was a place where the word undefined got put in the standard. That says, well, either vendor A's way of doing it or vendor B's way of doing it's okay. We don't really care which one, most people don't care, but there is a slight discrepancy there. Private data is one of those places where there was differences in how it's implemented, which is why it's officially defined as private data is undefined both on entry and exit to the particular parallel region. That's part of the memory model. Each thread only has a temporary view of these variables, and if you want it synced up globally, you need to use the flush pragma. So let's illustrate this. Words don't do this justice, so let's give a picture. So in a shared memory system, you can access variables by multiple threads. You may have thread A accessing the variable x in a couple different ways. It initializes it to 0, and then sometime later it sets it to 1. That's just two simple memory writes. You might have thread B, that it's reading the value of x, and it's sort of waiting for thread A to signal that it's done. So this is a case where the program's rolling its own synchronization. It's assuming that I can communicate between different threads without going through the existing OpenMP synchronization constructs. So there's no OMP try-lock, OMP set-lock, there's no critical, there's no atomic. And the question is, what in the world does this mean? Well, unfortunately, hardware doesn't agree as to what this means. So there had to be a little bit of convention introduced into the OpenMP language to force it to have a meaning across different hardware implementations. And here might be a more explicit way of doing this, which is just say, I'm waiting on a flag variable. How do I make sure I'm actually reading a value that's not stale, that I'm reading the value that another thread wrote, and that the compiler didn't optimize away my reads, and basically I'm spinning on a register instead of spinning on a memory location. So the flush pragma is the way users can control this, which is to basically tell the compiler, keep your hands off of the variables here. Something weird is happening. Another thread is possibly writing to memory. I need the real value from memory, not the value you might have cached into a register. So putting flushes periodically allows the system to do this. And as I said, if you need to do this, you're probably writing your own synchronization, and you should be asking the question, why am I writing my own synchronization instead of using what the system has? There are some good reasons, but you should at least question yourself to say, is that really what I want to be doing? So the flush acts as kind of a memory fence. If you've been in any architecture classes, if a machine does not implement sequential consistent memory access, which pretty much no machine implements, some of them implement kind of right ordering consistency, others are more of an explicitly relaxed consistency. They are the points that these fences occur, and to make sure that any write which has been posted before the fence is then visible to all threads after the fence. Normally you don't need to use explicit flushes because they're buried in the other constructs implicitly. Every time you enter and exit a parallel region, there's an implicit flush in the implementation where it's just doing it for you. Anytime you have an explicit or an implicit barrier, the flush is already there, you don't have to do it for you. entry and exit to critical sections, entry and exit to locks. All of those have implicit flushes where the compiler knows that it has to get memory in a coherent state at that point, and it's not allowed to optimize across those points in the program. There are a couple places where there are not flushes. One of the ones which is a little bit surprising is on entry to a worksharing construct. There's no requirement that if there's a race between the setting of a variable before it and the use after, that isn't there. And on entry and exit to a master region, there's no flush implied either. A lot of this talk about flush is if you are familiar with relaxed memory architectures, if you know about Itanium or PowerPC, those are two very popular relaxed memory architectures. Alpha was another one from a few years ago. You have to be very careful about how you build synchronization in those systems and how optimizations trigger. OpenMP by design has built in these implicit flushes to most of the constructs, so you really don't have to think about it unless you're trying to write your own runtime system in OpenMP, i.e. write your own synchronization. So this prevents the compiler from doing optimizations that would break your code in ways that are hard to debug. And in general, it's part of the design of the system that just works. Flush does have a list. It's usually discouraged to use a list because people use it wrong. It's harder to use it right than it is to use it wrong. So if you're going to use it, flush everything, because pointers, variables and pointers to variables, you might get confused about which one you're flushing. And as I said, this is a very advanced topic that if you want to do this, working with the compiler implementer to figure out the right way is probably a good thing to do here. Okay, that's enough negatives there. There is one other recent announcement that I might talk about a little bit, and this is, I mentioned I was privileged to work on the first OpenMP implementation. I'm privileged to announce that implementation in its current form, which I think is on generation 10 or 12 or something since then, has been open sourced. So if you're actually interested in how an OpenMP implementation works, what it takes to actually build up some of these primitives, to build synchronization, thread dispatch, work sharing, it's available at openmprtl.org. It's the same implementation that is shipping as part of the Intel Parallel Studio. So it's known to have pretty good scaling characteristics and pretty high performance across a wide range of at least x86 hardware. One of the reasons why we wanted to get out there is we saw OpenMP getting into a few more implementations like LLVM and CLang, and wanted to have the best implementation available for them to choose from. So it's there on the website if you're interested in some of the gory details of how this stuff might work internally. Okay, so to conclude, we've covered some of the more advanced topics of the OpenMP language, some places where the hardware that OpenMP runs on shows through and you need to control it. I've specifically not covered vendor-specific extensions. There may be places where you have to use them. For example, thread affinity, thread pinning is a place where practically right now you have to use vendor-specific extensions. Hopefully in the future that will all be standardized, but it's going to take a while for the vendors to actually implement the new standard and get it out there. We talked a little bit about the notion of arbitrary task creation. Sometimes you need to get your job done and it just doesn't fit in a simple loop. A lot of the new algorithms people are coming up with are very dynamic. They're not your father's, grandfather's, grandmother's type of scientific computing. They're messy, they're weird, they're really optimal and powerful, but you need more powerful techniques. OpenMP can now give you some of those techniques. As I said a couple times, I started out writing an OpenMP library. I've been working on tools since then. I'm hoping in tonight's section to walk through one of those tools, which helps you figure out, given you've got a piece of code, where and how might you want to put OpenMP into it. So we'll make some machine problems available so that you can play with OpenMP in a bootstrapped fashion, and then walk through a mini tutorial on what capabilities that tool might have. So thank you very much, and I can take questions.